Let me try that again. Good morning and welcome to the International Workshop on Quantified Boolean Formulas and Beyond, or simply the QBF Workshop. We have a mix of talks and a little bit of discussion at the end prepared for you. And we'll start with indeed 2 talks on problems beyond QBF, even if only slightly. We'll be hearing about dependency quantified Boolean formulas. And our first speaker is Roland Chang from the National University of Taiwan. And he'll be talking about something that I first heard about by my colleague Tony Tan from Liverpool. And I'm very excited about this work. And yeah, please take it away. Well, I think we'll just, in case there are people that are watching this online, if you have a question, maybe wait until the mic reaches you so that we can record the question. We are streaming this. Oh, yeah.
Okay. Can you hear me, Yang Nai? Okay. Yeah. So, sorry, I try to make it a full screen. Here. Okay. Yeah. Hey, let's resume our talk. Okay. Maybe for the online participants, let me quickly introduce again. This is a joint work with my students, Long Hing Feng, Che Zheng, and Yue Fan, and Tony Tan. And Tony now is a professor at Liverpool as a colleague of Friedrich. And so let's see our outline here is first I will give a quick introduction and motivation. And then we will talk about how to solve 2D QBFs. And then talk about how to extract Scholem functions. And also then I will show some experimental results and finally conclude this talk. So first let's define what is KD-QBF. So a dependency quantified Boolean formula, usually we can write it in this premix form. For all x1 to xn, there exists some y1 over variables z1, yk over zk, and phi is a Boolean formula over these x and y variables, where zi is essentially a subset of the for all functions. And we say we call it dQBF is k with k essential variables. Then we call this dQBF as k dQBF. And it has been recently shown that there is a strong connection between k dQBF and k set. You can think about k dQBF is a succinct version, exponentially more succinct version than k set. And 2D QBF is a special case where the complexity is p-space complete. And 3D QBF is already in the full EXP time complete category. And compare with 2 set and 3 set, they are in the NL and NP complete complexity respectively. So, and there are parsimonious reduction from arbitrary DQBFs to 3D QBF. And there are some previous work showing that we can leave some type of reductions from set to language of NP and to reductions from DQBF to language of NEXP. And in this talk, we will focus on the special case of the p-space complete to DQBF. And what's the motivation why we would like to look at this special case? First of all, it's easier than the NEXP time complete general DQBF. And it's an alternative of QBF formulation to encode the p-space problems. And essentially, we will show 2 applications, and they are easier to encode in terms of 2D QBF rather than translate it into a QBF formulation. And so currently, we don't have a clear way to efficiently convert between QBF and 2D QBF. I mean, efficient, of course, we can use the Turing machine operation to encode it into a QBF form, even for doing this translation. But we consider it as not effective, practically efficient. And so on the other hand, solving 2D QBF, if we can do it nicely, then possibly we can try to generalize it to solve general DQBF. So they will give us some insights. And so here is the theorem. We are given the KDQBF formula, and where phi, the matrix, is not necessarily in the CNF form. So this KDQBF can always be transformed into a KCNF psi, such that psi is satisfiable if and only if the KDQBF phi is satisfiable. So the conversion is easy in terms of the following construction. So we are given this KDQBF, and here for each yi, under the assignment A project to zi, and we can consider yi of ai as a new variable. So we denote it as xia, and then we can let psi be in the conjunction of a set of clauses, where if we have A, B assignments to X and Y, making phi to be false, then the corresponding, we can construct a corresponding clause of literals, where if BI is true, then we have the literal XI. If BI equals false, then we have not XI as the literal for this L. So now we can construct this CNF formula. So as you can easily see that if K equals 2, then this CNF will be just simply a 2 CNF, right? And so the 2 CNF psi is satisfiable if and only if the implication graph does not contain a cycle containing both L and not L literals for some literal L. So we can determine the satisfiability of a 2D QBF if there is no cycle containing this. So we call this as a best cycle on the implication graph. So and recall that the 2 CNF, we can solve it by the following way. We can first construct, so solving 2 CNF is easy because we can just use BCP, Boolean constraint propagation, without having any assignment to the variable. And we can determine whether the formula is true or not. So basically, if we construct the implication graph, and then we can check whether in this implication graph, all the strongly connected components contains a literal and its negation. Okay. So if it contains such a both literals, then the formula is then the formula will be for unsatisfiable. Okay. And so it is not practical though to construct such an implication graph. So we would like to use another method to determine the satisfiability of this 2CNF. So we can think about we try to convert the strongly connected component computation as a reachability computation. And this is something people already done in, let's say, converting a liveness property into a safety property, right? In liveness property model checking, we want to detect whether there's a lasso shape, there is a cycle, right? And you can convert this into a reachability formulation. So the way is detecting this cycle from starting from L0, and at some point we encounter not L0, right? And then there are some other implications back to L0. So this kind of cycle we can reformulate as a path from L0 to somewhere we change the phase and then back to the L0. And what we can do it is we enlarge the state space, right? We use two literals, L and L prime, where L0, L prime try to denote that is the starting point. And then we try to evolve L0 in a second argument here. And whenever we evolve to not L0, right, we then would use the first bit as a flag to denote we already encountered this negation. And then we again evolve, and if we can eventually back to the 1L0, L0 state, then we know we have this cycle, base cycle that we already encountered, right? So now our state transition system will consist of the triplet, right? There is the first flag bit, and then there are two other assignments denoting the initial starting state, and then the evolving state. And by doing that, now we have a state transition system. So the state is denoted by this, the first bit is 0, 1, and we have other L and L prime, where those are the literals in our previous discussion. And then the initial state will be starting from 0 and L, where L and L are free variables, essentially, right? And then the state transition system will be, there is a BL-L0 transition to BL prime L0 if this implication is on the implication graph. And there is a transition from 0 to 1. And for the second and third arguments remain the same. If L equals not L0, then we would do this change. And the property is we want to ensure that this kind of 1L0, L0 state cannot be reached from the initial state. Okay, and we know that the reachable state would represent an edge from the implication graph, from L prime to implies L. And the transition closure of this implication graph would denote it as the G bar. Essentially, G bar will have all the edges that representing the transitive closure of G. So then how to determine whether there is such a transition? Basically, we just check whether the corresponding A and A assignment, B prime assignment will make the formula to be false. So here is the more detailed construction. So essentially, we would use some registers, some bits to denote the transition. And where this R1 is the previously we say the flag to denote whether we encounter the negation state. And then K, B, and X denoting the index. Here is the case Y variable, and B is the correspondingly negated literal or the positive literal. And X is the assignment for the X variables. And KT, BT, and ZT are the corresponding bits that are recording the initial states, the starting state. So the previous intuition can be converted into these more formal formulas in terms of the initial state, the transition predicates, and also the property predicates. And to solve the reachability, we can quickly introduce what are the corresponding consequences of whether a reachable reachability analysis, what will give us in terms of its answer and certificate. So, so if we are given the state transition system with the initial state I of X and the transition relation T, property P, so if the property will be violated, right, then we can get a trace. Then they can satisfy, starting from X0, we can transition to some Xn, all the paths will satisfy T. And if the property does not, will not be violated, then the solver will give a Boolean formula, S of X. This is an inductive invariant, and that will satisfy the following three properties, right? That is, I of X implies S of X. That means S of X will contain the initial states, and it's closed under transition. That means if we X is in the current state, under the application of the state transition, then its next state also satisfy S, right? And then the last criteria is P holds on all the S states. So this is a certificate if P let's say if P always holds, right, then we would have this property. Okay. And in order to solve the reachability, there are many different model checking algorithms that we can use. For example, we can use K induction or use interpolation or property-directed reachability. And we choose property-directed reachability algorithms because it is one of the most efficient way to do the reachability analysis. And we would use the two solvers. One is AVR, the other is PDI command in ABC. Okay, and the S can be viewed as a set which contains all the states reachable from I. And because for these solvers, it's not exact reachability analysis. So it will contain some over approximation of the reached state set. And so here, let's look at this simple 2D QBF example. Although this 2D QBF is also a QBF, but let's just try to make our state transition, this implication easier to understand. So essentially, this matrix we can write in terms of convert it into the CNF form. It would become this 2 CNF, right? So for each of the clause will be corresponding to an implication, an edge in this picture here. Okay, so essentially there are 8 implications because each clause will contain 2 implications, right? And let's say, assume let's apply reachability analysis on the previous 2D QBF. And possibly we will get a final S, this over approximated state set. And it will contain these edges, including the black one, the original one, and some over-approximated edges shown here in red. Okay, but so the problem now is how do we already can use PDR to answer the question whether the 2D QBS is true or false based on reachability. But the next question we further want to compute is the certificate. Right? We just not satisfied with the answer of yes, no. We would like to compute some certificate. And what we would like to do essentially especially for true 2D QBF, because ideally we can compute the corresponding scalar functions for the existential variables. Of course, we can also talk about if the reachability is false, is non-reachable, then essentially, ideally, we can convert some resolution proof to show that the formula is indeed false. But more particularly, we would like to more interested in the satisfying case, the scalar function. Okay, so let's recall the previous more straightforward approach, right? In terms of the 2CNF case. So in 2CNF case, we can check the implication graph and check whether the strongly connected component contains L and not L. And if we want to construct a scalar function, we can build a cyclic graph by constructing the strongly connected component, and we can condense the SCC into a vertex, and the implication graph may become a directed cyclic graph of these SCC components. So and later what we can do is we can base on the reverse topological order of this directed cyclic graph, and then for each of the strongly connected component, we can find a consistent assignments to the variables, and then we construct that according to the reverse topological order. Then we can find the consistent scalar function assignment to the formula. So again, this is the basic idea how we can derive the scalar function from the assignments to these literals. But we would like to translate this in terms of back to our reachability using PDR. So essentially, in the implication graph, we can divide the graph into two parts. One is those parts where there is a x implying x to not x implication, or not x to x implication. And there is another part where these two implications are not edges. So for the upper part, that means we need to force the assignments x with 0 or 1. And for the later part, that means it's a don't care. X can be 0 or 1. There is a flexibility to choose x to be 0 or 1. Okay. But there is a consequence. We cannot choose any one. We need to make it consistent in terms of the scalar function certificate. Okay, so let's let G bar be the transitive closure to our implication graph, and then S be an over approximation of G. Then if L1 imply L2 is in this S graph, L2 imply L3 is in the not G graph, then L1 imply L3 should be in the S in the S. We call this as being a valid over approximation. And essentially, here is the table try to summarize from whether the edges, these two edges are in G bar. Then the formula here, whether in S we have true or false with respect to this conjunctive formula here. So essentially, to conclude, if we have just single edge implication in the G bar graph, then we always can uniquely determine what is the corresponding true or false. And if both are true, this is not allowed because we already know we already have a certificate proving that the formula is already false. Then that means we have the reachable to the completely true. That the best cycle exists. So this will not happen. And for this, if these two edges are not in G bar, then we have the choice. So then we have this. If FIA, let's say, make it to be this formula. So this basically, we would like to check whether not phi x, the original formula and y1 equals f1, y2 equals f2 is not satisfiable. So basically, we can use the returned Scolen function, substitute back to not phi, and try to check whether it's satisfiable or not. If it's satisfiable, that means we have a counter example showing that this is not a valid Scolen function. And then we would analyze the implication graph with the corresponding 4 vertices involving not x, x not x, y, and not y. And we would know that x cannot reach not x, and y cannot reach not y. Okay. And then we would force the assignment of x or y by adding one of the 4 implications into the implication graph of G. Basically, we would enlarge the graph G by adding 1 more edges. And we would repeat this process until we find a solution of the Scolen function. So here is one example, the previous example. So suppose S returns, we have this over-approximated state graph, over-approximated implication graph. And from this, we can possibly give the function of f1 equals 0 and f2 equals 0 as the Scolen function from this implication graph. Okay, because let's say f1 equals 0. So that would mean we would assign this to be true. Right? So this is for f1, and here is its value is 0. If we assign this true, essentially there won't be any best cycle appearing. So this is a valid Scolen function. And for f2 equals 0, f2, if we assign it equals 0, then this not x2 0. I'm sorry, I think I make a mistake. If this is 0, assigned to be 0, then implication is this direction, right? And f2 equals 0 means f2 assigned to be 0 is false. Then we will have another implication happen here. But in any case, there won't be any complete cycle. So this is a valid Scolen function. Okay, so by the previous analysis, now we can the involving 4 literals, we can add one of the edge. So let's say if we add this edge, then we can derive its transitive closure. Correspondingly, we will have this closure here. And here again, now we would have the other can possibly have these over-approximating edges here. So in this case, the corresponding Scolen function we will derive. The S will inform us to give us f1 equals 0 and f2 equal 1. And essentially, this will be a correct Scolen function. So now we can stop. So here is the overall flow. So I would simply skip. And the following, I will introduce the experimental results. So here we study two cases. One is the partial equivalence checking, or equivalence checking for partial design. And the other is two colorability. So, and we compare our method with three DQBF solvers, including DQBDD, HQS, and patent. And also we develop our solver with two different PDR engines, AVR and ABC. And we test, all the tests are performed on this machine. So for the first test case, basically, I think I will skip this because this is more detail about how to use ABC to solve the reachability, where we need to enforce ABC will take only the single initial state transition system. So we need to perform some trick in order to apply ABC PDR. But I will skip the details. And the first benchmark is essentially given the Boolean circuit, and then we carve out two places where this becomes bread boxes. And we would like to answer whether we can synthesize these two bread boxes where it can equivalent to some specification. So essentially, we got this kind of formulas. And then here are the experimental results. So so here are the set instances, and on the right-hand side, those are the unset instances statistics. So as we can see that we can solve for the red one is the 2DQR, our approach based on ABC engine. And so the second blue one is the 2DQR based on AVR. And the solid and the dotted version are correspondingly whether we try to derive a Scolen function. So in general, there are some overhead to do the Scolen function computation, but they perform very, very similar. And the following different DQB-DD are solving at this level, about 460 cases. And HQS similar. And pattern in this case is not solving as good as other solvers. And for the unset case, it's very interesting that pattern becomes very good at solving these cases. And the performance is very similar to 2DQR ABC version. And so here is the HQS, here is DQBDD. So there are interesting characteristics for these different solvers. So maybe later, if you have any questions, I think Frederick can maybe give some insights. Okay, yeah. So here are some plots where compare different solvers. For the for example, for DQBDD compared with ABC and AVR, here are the statistics. It's the same as the previous plot, but we based on each case, we can see it compare two different solvers. And as we can see, what we can say is there are many cases where DQBDD times out, and that is why in the previous plot, right, the sub cases DQBDD is not as high as the 2DQR. And for the easier case, DQBDD, we can also observe it solves faster than 2DQR. I think 2DQR has some overhead to convert into some reachability. It has some performance overhead. But for the harder problems, it seems to pay off to do this kind of reachability analysis. So on the other hand, we should know that DQ, let's say DQBDD, pattern, HQS, they are general DQBF solvers. And our 2DQR is specialized for 2DQBF. Okay, so this is also something we can think of that to specialize some special DQBF formula can be beneficial. And these are the unset cases. Okay, I will skip this. And these are the just simple AVR ABC comparison. And we can see that in general, ABC version of PDR engine is more efficient in these cases for solving. Okay, and here are the in terms of Skoglund function size. And the conclusion is the ABC version computed Skoglund function in terms of ARG size is in general larger than other solvers. And okay. So let me check. So the ABC flag version, if we have this, the ABC flag is better. Okay, so these are showing that the 2DQR ABC flag version seems to be better, right? So in any case, you can do the analysis from these plots to see what are the statistics. So the second experiments we done are on these two colorability problems, and the corresponding formula is look like this. We have some color, and then we need to enforce that if the two Y and Y prime they have an edge to connect it, then their colors should be different. Okay. So here are the corresponding statistics for the results. So here is the runtime. So lower is better. And here are the number of bits we generate the set and set cases for the directed graph. And with bit size k from 2 to 127. And that means the graph, we have 2 to the power k vertices in our graph. Okay, and the solver are given 600 seconds for solving. And here, as we can see, that the 2DQR ABC version performs the best, followed by AVR version. And then we have these unset cases. It's also similar, but not as stable as the set case. So to conclude, we introduced an algorithm to solve 2D QBF and with the certificate derivation capability. And our method in our studied two test cases, they outperform the state-of-the-art DQBF solvers. And we hope to extend our methods to develop general solvers for DQBF. Thank you for your attention.
Yeah, thank you very much for this nice talk. Do we have any questions?
Do you have any insights how this approach connects to proof systems? Is there a connection, for example, to resolution or?
Okay, I think for the reachable, if the 2D QBF is false, then that means in the reachability we will have if it's false, then indeed we are reachable. to the back cases state. And in this case, I think we haven't done that, but we think we can try to make it as a resolution proof, and perhaps that it would connect back to the proof system in terms of that way.
It
Yeah.
sounds a bit like maybe there is also something dual.
Yeah, that's our future work. We haven't done that, but there's something in our plan.
Because also the column function extraction algorithm sounds a bit like the work you did for Q resolution. Also there might be some connection.
Yeah.
Mm-hmm. Okay.
Yeah,
Thank you.
So I walked in a little late after your session started. So what is the complexity for, what is the decision procedure complexity for 2QBF, for 2D QBF?
It's two P-space complete.
It is P-space. Okay.
Space complete, yeah. And the 3D QBF is already an EXP time complete.
I see. Okay.
Yes, so I wanted to ask related to this, it's not really from this talk. So 2D QBF is P-space complete, but have we looked at something like DQBF with Horn? HornSat is P complete, so it's harder than 2 CNF sat. So similarly, HornSat inner matrix with DQBF, do we know what is the complexity?
I think they would correspond to EXP time, deterministic EXP time complete.
Okay.
Yeah.
So you mentioned that.
So it's the home crows, right? The home crows form. I think it corresponds to. I think in the previous work, in the previous work. I think Tony, in his previous paper, they might, I'm not sure, they might have talked about this in their paper, but I need to check. But recently, we have some discussion about that internally, yeah. Yeah,
so I mean, P-space and NEXP, that's quite a gap, right? From 2D QBF to 3D QBF.
Yes.
So in your final slide, you mentioned extensions to general DQBF. So reachability would not suffice, right?
Yeah.
So,
we are thinking that similar to BCP is an essential component for the set-solving. And so here the 2D QBF may be considered as a engine where it can be called for a larger DQBF system to solving. So that is one of the intuitive ideas. Maybe we can do some generalization for solving general DQBF.
One more question.
Sure, go ahead.
So you said from the ISCAS 89 benchmarks, you created your benchmark instances, right?
Okay.
So I'm just wondering, why are there a lot of 2D QBF instances coming? I mean, is there something which makes 2QBF very common very easy to derive from the circuit benchmarks?
These two applications are particularly very naturally can be formulated as 2D QBF. So here are the let me see. So here is a design circuit with two black boxes. Right? So it essentially says for all these X assignments, and then we have two black boxes in terms of their corresponding dependency sets. Then we want to check whether these black boxes can satisfy some specification.
Yeah, but I guess in general, there won't be just two black boxes. There'll be many more black boxes.
Yeah, it's not general, right? If you have 3 boxes in general, then it becomes
so you used some criterion to choose two of them to make them black boxes, because the circuit would probably have
arbitrary. You can choose arbitrary. And they can share even some overlap support sets, the input variables.
Okay, maybe one last question.
It's a quick question. I'm curious about this column function sizes. So have you compared the column function sizes with the other approaches? So this one?
Let me see. Column function size is this plot.
So
So
sorry.
we compare. Yeah.
I see. So yeah, it's a bit curious because in QBF solvers, we have seen different solvers generate different size of column functions. I mean, you need these functions to verify you want to use it, right? So it would be interesting if the solver can produce compact forms.
Yes.
Because you focus on 2 DQBF.
Yes. Yes. Yeah. So here I should mention that pattern in this case does not perform well is compared with others is because pattern somehow the circuit size is larger, and here we don't apply we cannot apply a flag to minimize it, so it's will be larger. And for other cases where flag, the optimization command can be applied, so it's smaller. So this is something special here compared with the other plots.
Okay, then let's thank Roland again.
Thank you.
Yeah, our next speaker is my PhD student, soon former PhD student, Franz Reichel. I feel like I chaired at last year's workshop. I also chaired the session where you gave a talk. And Franz will be talking about extensions of our DQBF solver patent in this talk.
Okay, so hope now everything works. So yeah, hello everyone, and thanks for the introduction. In the following, I would like to talk about some ongoing work on a new representation of candidates column functions in our DQBF solver patent. So can you hear me? Is it working properly? Okay, and yeah, this was joint work with Friedrich. So even though you already heard what a DQBF is in the last talk, I would just like to give a brief recap of which kind of formulas we are considering. So you see that we are using formulas in Brennick's conjunctive normal form. So this means formulas consists of a propositional matrix in C and F and of a quantifier prefix. And you also see that we have formulas in S form. So this means so this is not working, this presenter. Okay, now. Yeah, so each existentially quantified variable is equipped with a dependency set. And yeah, now we ask if this DQBF has a model. So this means we want to find a column function for each existentially quantified variable, where this is just a function assigning true values to assignments for its dependency set. And then we require that if we replace the existentially quantified variables by these column functions, we want to obtain a formula which evaluates to true for each possible assignment for the universals. So this is here obviously the case, so we can plug it in, and then it will always assign to true. Okay, so I just want to keep this introduction short because you already saw what a DQBF is. So now let me really start. And so the idea to solve DQBF, I would like to talk about this heavily based on expanding DQBF. So I would like to give a brief recap of expansion based, so the idea of expanding a DQBF. And so for this purpose, sorry, the laser pointer doesn't really work sometimes. So we use the same DQBF as before. And now to check whether this formula is satisfiable, so this means if it has a model, we can try to transfer it to a propositional formula. And for this purpose, we can instantiate. So you see this formula to be true. then for every possible assignment of the universal variables, we must find some assignment for the existentials. And thus, we can instantiate the propositional part with respect to all possible assignments to the universals. And then we just conjoin all these instantiated formulas, and then we can check the resulting propositional formula. So in this case, if we instantiate the matrix, we get the following formulas. So here note that we use these annotations because, of course, the extensional variables may attain different values for if the dependencies are assigned differently. So for example, here, if U1 is false and if it is true, we want to be able to assign them differently. And thus we add this annotation. And this means that these two variables are considered as different. And now we can check whether this conjunction of this formula is satisfiable. Yeah, and indeed we can find a satisfying assignment. And from this we can then obtain some Column functions. So this describes some. We can also show unsatisfiability. So for this purpose, we add another clause to the matrix. In this case, in the instantiation, we get these clauses. And now you can see that we can resolve the first unit clause with the first literal here and this with this. And thus we can obtain the empty clause, which means the propositional formula is unsatisfiable. And from this, we can conclude that even the DQBF is unsatisfiable. Because for this universal assignment, we know we cannot find, so for this, we cannot find an extensional response which satisfies the matrix. Okay, so, but now, of course, a problem with this expansion is that, you see, if we have, it grows exponentially. So we have to consider all the universal assignments. And for this purpose, we don't want to consider all the instantiations. And yeah, this is one of the ideas in patterns. So we would like to incrementally refine some candidates column function based on some counterexamples to an candidates column function. And yeah, so I would like to start with giving the idea, and then I will discuss the details of the algorithm. So for this purpose, let us consider this formula. So here the actual matrix doesn't really matter. So we are mainly interested in the prefix. And now we assume that we have some candidates column function. So this is some set of rules which restricts the set of all possible functions. And initially this we allow any possible functions. So we say it can be arbitrary. And now we look for a counterexample which is consistent with this model. So a counterexample is just an assignment of the variables which falsifies the matrix. So for example, here we say that this assignment shall falsify phi. And now we want to use this counterexample in order to refine this set of constraints which restricts the Column functions. And as I said, initially this rules are empty. So initially we allow any function, and now we want to refine this. And for this purpose, we use clauses of the following. We can use clauses of the following shape. So here you can see. So we have here these annotated variables. And if we now fix the assignment of this annotated variable, then under this, so you see here, the assignment for E1 is just U1 and U2. So under this assignment, we can then fix the assignment of E1. And similarly, we can fix the assignment for E2. Now this gives us a way to fix E1, but of course, we don't want to fix it to an arbitrary value. We have to, we want to fix the counterexample. And for this purpose, we have to find a suitable assignment for these annotated variables. And now the idea is, so you see the counterexample only occurred because E1 was assigned to true and E2 was assigned to false. And thus, we want to either assign E1 to false or E2 to true. And for this purpose, we use the following clause. And we ensure that for these annotated variables, we use an assignment which satisfies this clause. And by doing so, these four clauses would not allow this counterexample. Yeah, this is repeated. So then we look for another counterexample, which is consistent with this previous set of clauses which we derived here, and this satisfying assignment. And then we do the same. So we introduce another set of clauses. We add a new clauses with these annotated variables, and yeah, we continue this. And yeah, now to clearly distinguish between existential variables and these annotated variables, in the following I will call these variables just arbiter variables, and I will call these clauses, so these clauses consisting only of these annotated variables, as arbiter clauses. Okay, so how does the algorithm now really look like? So the algorithm, it takes an dQBF with a prefix q and then a matrix phi. And then we initially, so this model is the set of clauses. This contains these clauses. So here. Initially, we initializes it as the empty, as the set containing no clause. This set of arbiter clauses is also empty initially, and also this arbiter assignment is the empty assignment. And now the idea is we check whether we can falsify the matrix with an assignment that satisfies this current representation of this model. If this is satisfiable, we can get a model, which is a counterexample. So this shows us why this model is not, so why this current candidate cannot be a model. But now in this candidate, usually we also have existential variables which assign the correct way. So not all of the existential variables in this counterexample are assigned in the wrong way. So we want to find only those variables which really got the wrong assignment. And so here the idea is that we know that phi is falsified under sigma. So we can look for a subset of sigma which suffices to falsify phi. And from this, we can then restrict this subset to the set of existential variables. And this gives us some subset of the existentials which are assigned the wrong way. And we know that every existential variable which is not contained in the sigma head is assigned the correct way. And we don't have to refine the candidate's column function. Okay, next we introduce the these clauses I showed before. So we can introduce for each existential variable in the sigma head the annotated variable and the corresponding clause. Then we introduce this arbiter clause, which ensures that we don't repeat the counterexample. We add it to the set of all clauses. And then we have to look for such an arbiter assignment, which fixes the response of the existential variable. Yeah, and for this purpose, we look for a satisfying assignment of all the arbiter clauses. And so the idea is, so if we can satisfy this clause, this set of clauses, this satisfying assignment ensures that under the clauses here, we don't repeat any counterexample which we showed before. So if on the other hand, this set of clauses is unsatisfiable, we know that we cannot repair all the previous counterexamples. So every possible arbiter assignment would repeat at least one counterexample. And this means that we cannot find a model. And indeed, we proved that each of these arbiter clauses can be derived by for all x plus res. And thus, if this formula is unsatisfiable, we really know that there cannot be a model. Okay, so let's briefly illustrate this with an example. So you see the same formula as before. We initialize the variables as told you here. Then initially the candidate is empty, so we can allow any counterexample because we have not yet any constraints. So we, for example, get this assignment. This falsifies the second clause and it satisfies the first and the third clause. So you can see that this variable e2 only appears in the third clause and this is satisfied. So it's assigned the correct way. Okay, what happened now? Okay. Thank you. Okay, so we get this assignment and we see that this variable E2 is assigned the correct way, so we can remove it for this for sigma hat. Then we introduce these clauses I told you before. We introduce this arbiter clause. We add it to the set of all arbiter clauses. Then we look for a new assignment for this satisfying assignment for these arbiter clauses. And then we just repeat this. So we look for another count example, which is consistent with the current candidate model. And we repeat this procedure until either the arbiter clauses become unsatisfiable or this subcheck yields unsatisfiability. And in the end, we can here see that if we instantiate these clauses with this arbiter assignment, then the resulting clauses cannot be satisfied by any assignment that falsifies the matrix. And this means that these clauses, together with the arbiter assignment, indeed represent a model for the DQBF. Okay, but now while this algorithm is sounding complete, so a problem is that so it lacks some generalization of this universal part. So you saw before, we can try to generalize the existential part. So we can throw away existentials from the count example which don't matter, but we cannot throw away the universal variables because in the annotations, we always have total assignments. So always all of them are used. And so why is this a problem? So let's consider this formula. And you know that we look for some count example. For example, this assignment is a count example because this clearly falsifies here this equivalence of the two variables. So this means we introduce this annotated variable with the corresponding clauses. Next, we get this count example. But now this variable only fixes the extensional response for this particular total assignment of the universals. And this means if you now flip the assignment for U2, we get more or less the same count example again. And thus, in the end, we have to consider all the universal assignments, even though here only U1 appears. And yeah, this shows that we cannot really generalize the universal parts of count examples. And now the idea is to use partial annotations for these arbiter variables instead of total annotations. Okay, so maybe the first idea would be to just, so if we have an count example, we could just reduce the universal part similar as the existential part. And then we could just use this universal part for the annotations. But here you can see that this doesn't work. So you see, obviously, to falsify this clause, we only need a U1, and here we only need U2. So we can reduce these assignments. And now we could think that we could add these, we could use these partial annotations. But now the problem is, if we would assign, for example, these two variables differently, then under the assignment which maps both U1 and U2 to false, these clauses would be very unsatisfiable. Because you see, these clauses cannot really coordinate. If we have if we assign both of them false, then these two literals are falsified. And if we assign the annotated variables differently, we would need to assign E both to true and false, which is not possible. And so we cannot satisfy this model, and this would mean that the model itself would be inconsistent. So it would not describe any function anymore. And for this reason, we have to proceed differently. So we start with the algorithm I already showed you before. And now this is the real new part. So before, this is the current part. So we use this total annotations. And now this improved part is, so this new version is to use these partial annotations to allow a high degree of generalization. Okay, now the idea is that we already start by initializing for each example an arbiter variable with an empty annotation. So this means the empty annotation fixes the value of the existential variable no matter how its dependencies are assigned. So this is some over approximation. And then, similar as before, before we reduce the existential part of the count example, now we also reduce the universal part. Now, moreover, we don't always introduce new annotated variables. So we only want to refine them if necessary. So we would like to use small annotations as long as possible. And only if we see that this is not enough, we over approximated the whole thing, we would like to split the variable. But we don't want to introduce new variables at each step. So I will talk about this later. Then also for these arbiter clauses, we don't use total assignments. So before you saw that we always just projected the count example to the dependencies. Now we proceed differently. So if we have these arbiters, so we have some tree-like structure where we have the annotations, so we can more or less classify the assignments to the dependencies to different arbiters, and then we just take. So you will also see this later. We can classify the total assignment to some partial assignment, and then we use this partial assignment as the annotation. Okay, then last but not least here, if these arbiter clauses are unsatisfiable, we now no longer know that there's indeed no model because we have this over-approximation. So as said before, we start with the empty annotation. And this already means that we assign the existential variable the same way, no matter how the dependency is assigned. And of course, yeah, this is not the way how a DQBF works. So the variable must be able to attain different values. So if this is unsatisfiable, we have to pay some special care. And for this, I will discuss here. So in the first case, so here we assume that we have some set of arbiter clauses which are unsatisfiable. So here we have the following count examples and the following blocking clauses. You can see that this as arbiter clauses, you can see that they are unsatisfiable. So you see we get can derive the empty clause. And in the original case with total assignments, this immediately meant that the DQBF is unsatisfiable. Now we have to do some extra work. So namely, we log for every count example the reduced set of the reduced universal count examples. So here, for example, we needed both universal variables U1 and U2. Here, only the universal variable U1 was enough to get the count example. Here we needed U2. So we now log each of these reduced count examples with each blocking, each arbiter clause. And then we check, do these assignments match? So here you can see for both clauses, U1 is assigned to true, so they match. And also here, U2 and U2 match. So what does this mean? So this means that for one specific assignment for the universals, we got the count example. And thus it doesn't really matter if that we assign E the same way for, so that E2 doesn't depend on U2, because we know only for this particular assignment for U2 we always get a problem. And thus it's enough that we have here this over approximation. Okay, so now we consider the second case where we have an unsatisfiable set of arbiter clauses. And here I slightly changed the formula. So we had here this negation. Now we get the following count examples, where here's again this reduced reason we computed. And then we get again a refutation. And of course, now we still have here this matching annotation. So for both these clauses, we had the same assignment for U1. But now you see that for this count example, we assigned U2 differently than here. So this means we have two count examples where we assigned the universal variable differently. But of course, this can be resolved by just allowing that the existential variable is assigned according to the assignment for its dependencies. So you know the variable may depend on an assignment for its dependency. And before, because we use this empty annotation, we always assign it the same way. So by specializing the candidate, we can resolve this problem. So this means that we can now split this variable. So we add these annotations, and this means that we can allow to assign E2 depending on the assignment for U2. And then this allows to fix this problem because you saw we have two different assignments for U2. And thus, yeah, the assignment can now depend on this assignment. And so by splitting these clauses, we no longer get a problem. Okay, so before I talked about how to split the variables, but we always also have these arbiter clauses which contain the annotated variables. And yeah, after splitting, they still contain the old annotations, but we now introduce new ones. And so what do we do with these clauses? So now suppose we have this arbiter clause, and now suppose we split the variable E1 according to this variable U1. So we found that the arbiter clauses were unsatisfiable, and we found that yeah, we have to introduce a split. Then we could, and now here we assume that the universal reason did not contain U1. So we can always, as I said, we try to reduce the size of this universal reason. And now you see U1 doesn't occur in this reason. And so this means we can derive both of the versions because, yeah, it's independent of U1. So we can show that both of these conditions must hold. On the other hand, if we make a split on a variable which is contained here, we can we know how to specialize it, so we don't need to consider the other case. And by doing almost finished. So we by doing so, we can now ensure that previously considered counterexamples are not repeated. But yeah, while this ensures that the counterexamples are not repeated, in our the test version of our solver where we implemented this, another approach worked better. So we just throw away all the arbiter clauses which contain this previous, so this old arbiter variables. While this means that counterexamples may be repeated, it helps us because you don't need to add a lot of copies of these arbiter clauses. And this worked better apparently. Okay, so now there are several things which can be done to improve this whole procedure. So currently, so it's important so to make the current to make good splits. For example, where is it, the count example? You see here, so if we would just split on U1, then we immediately know how to refine our model. But if we would start to split on UN and UN minus 1, it wouldn't help us at all, because then we make the wrong specialization. So we would get the same problem as now. So it's important that we add the correct splits. And there are several ways how we could achieve. So there are two specific ideas we have to do this. So first of all, we could try by sampling the initial matrix and then to learn some decision tree from this. And this gives us some way how the existential variable should be assigned. So of course, this doesn't really give us a model, but it gives us some indication how this tree-like structure should look like. And then we could initialize we could, instead of starting with empty annotations, you could introduce annotations according to this tree-like structure. Another version would be to, after some time, we could throw away all the learned arbiters, and then based on the count examples already seen, we could learn a new tree-like structure, which we could then use to introduce new annotated variables, which potentially have a better structure. Yeah, and last but not least, this is also a question for the audience. So we would be interested in some better way for selecting these variables right first place. So currently we more or less just pick some variable where the annotations do not match. But yeah, this is not always the best way. And so yeah, if we could improve the selection, this could improve the whole algorithm. Okay, so sorry, I'm already quite over time. So yeah, so this finishes the presentation. And so I would like to thank you for your attention, and I would be happy if you have any suggestions how we could improve this partial annotations. So for especially the selection of this split for these split variables.
Thank you very much, Franz. Do we have any questions before we go to the break? No? In that case, Franz will answer any questions offline during the break. Oh, I think we resume in half an hour, right? 10, 11. Oh,